In 1977, Airbus lent 4 aircraft to an American airline without charging a single cent. The project was bold and promised to revolutionize global aviation. The problem was that few people knew this same project was driving Airbus toward bankruptcy. A European manufacturer that had bet billions on a project nobody wanted in a market Americans had dominated for decades. There were no orders, production lines were nearly idle, and the window to change this scenario was closing fast. Facing enormous challenges and global skepticism, Airbus was on a desperate mission to prove its worth.
If you're also passionate about the world of aviation, consider subscribing to the channel and supporting our team. By the mid-60s, American manufacturers controlled more than 80% of the global commercial jet aviation market. Boeing, McDonnell Douglas, and Lockheed were the very definition of what a commercial aircraft should be, and the rest of the world bought what they sold. In Europe, the aviation landscape was chaotic. France had Sud Aviation, England had Hawker Siddeley, Germany had MBB, each with its own technologies, its own unions, its own vision of the future, and none large enough to compete alone against the American giants. But that was about to change. In 1967, European governments signed a formal industrial cooperation agreement. In '70, the Airbus Industry Consortium was officially formed. But here is the detail that most narratives about Airbus underestimate. The decision to create a consortium was not merely political, it was a radically new industrial model, unprecedented for its time in commercial aviation. The division of labor was remarkable. France was responsible for the forward fuselage and final assembly. Germany handled the rear fuselage. The United Kingdom designed and manufactured the wings. Spain took on the horizontal stabilizers. 4 countries, 4 industrial supply chains. The key to making it work was not just logistics, it was modular standardization. Each structural section was designed with strict interchangeability tolerances, meaning the industrial model created for the A300 could, with adaptations, be replicated for larger, smaller, or differently configured aircraft. Airbus had bigger plans. The project chosen for this challenge was a wide-body, a twin-aisle aircraft with a fuselage 54 meters long, a 44-meter wingspan, and 16 meters tall, capable of carrying between 240 and 330 passengers depending on configuration. And here lies the first paradox. Airbus did not choose this design because it was the safest. It chose it because nothing like it existed in the American market. The wide-body jet market had been inaugurated with fanfare by the Boeing 747 with its first flight in 1969. The 747 was spectacular, capacity for over 400 passengers, 4 engines, designed across every corner of the globe. But there was a problem. It was too large for many intermediate-density European and Asian routes. Its competitors, the DC-10 and the Lockheed L-1011 TriStar, the other 2 wide-bodies arriving in the early 70s, each came with 3 engines, a configuration that was expensive to maintain, complex to operate, and one that Airbus engineers were not willing to accept. The idea of a twin-engine wide-body was met with skepticism and, in some circles, outright distrust.
There was a concrete reason for this. Existing regulations restricted aircraft with only 2 engines to routes that never placed the plane more than 60 minutes from an alternate airport. This drastically limited where a twin-engine aircraft could fly. Crossing the Atlantic, for example, was out of the question. Transoceanic routes of any kind were, in practice, off-limits. And there was a deeper technical concern. The reliability of modern turbofan engines was still being demonstrated statistically. They were new. Long-term data was still being collected. And the perception, not necessarily the reality, but the perception, was that 2 engines represented an operational risk that 3 engines mitigated. Airbus engineers, however, made a different calculation. They selected 2 engines of the highest reliability class available, the General Electric CF650 and the Pratt & Whitney JT9D.
both high bypass turbofans with a ratio of approximately 5:1 between cold airflow and hot airflow, which made them not only more fuel efficient, but significantly quieter and subject to less thermal wear than previous generations. The higher the bypass, the greater the propulsive efficiency and the lower the fuel consumption per kilometer traveled. Less fuel burned per seat carried. That was the equation. But the boldest technical decision on the A300 was not even the engines, it was the wing. The A300 incorporated a supercritical wing profile developed from NASA research conducted throughout the 60s. A supercritical wing has a specially calculated shape designed to delay the onset of transonic shock waves, the aerodynamic phenomenon that at cruise speeds near Mach 0.80 generates significant drag and burns fuel. The conventional wing of the era created this problem. The A300's supercritical wing reduced it measurably. The internal structure of this wing was quite sophisticated for the time. Dual spars, semi-monocoque construction, and large-capacity integrated fuel tanks. But the detail few people mention is this: the wing was designed from the outset with structural margins for growth. It could support higher maximum takeoff weights, longer fuselages, and extended range missions. It was not a wing for the A300, it was a wing for a family that did not yet exist. And the advantages did not stop there. A technically superior aircraft does not sell itself. American Airlines operated entire fleets of Boeing, McDonnell Douglas, and Lockheed aircraft. That meant hangars, aircraft-specific spare parts inventories, maintenance contracts, trained maintenance crews, and flight simulators calibrated for those cockpits. Buying an Airbus aircraft was not simply signing a contract. The process was far more complex. The true cost of adopting Airbus was much greater than the price of the aircraft itself. And there was the lobbying. The American aerospace industry was, and continues to be, one of the sectors with the greatest capacity for political influence in the United States. Domestic manufacturers had privileged access to government contracts, export financing, and diplomatic support that no European company could easily replicate. All of this formed a wall, and Airbus was on the outside. While trying to scale that wall, the ground disappeared.
The oil crisis of 1973 had struck aviation with a force that few industrial sectors experienced so directly. Fuel prices quadrupled in a matter of months. The market fell into a deep recession. For Airbus, the effect was devastating. Between December 1975 and May 77, the consortium did not receive a single new order. Completed aircraft piled up in the yards of Toulouse without a buyer. Production was reduced to a minimum pace, just enough to keep the line alive. Internally, the discussion about the consortium's future had ceased to be strategic and had become existential. It was precisely at this moment that Bernard Lathière, president of Airbus, made a decision that would be discussed for decades. Instead of retreating, he went to the American market. With an unprecedented proposal, Airbus would offer 4 A300s to Eastern Airlines, one of the largest airlines in the United States, on a free operating lease for 6 months. No rent payment, no purchase commitment, with complete freedom for Eastern to return the aircraft at the end of the period if it did not like what it saw. It was a bet that would cost tens of millions of dollars in operational expenses. Eastern Airlines put the 4 A300s on its densest domestic routes. These were not easy routes. They were the ones that demanded the most in operational efficiency, regularity, and reliability. The airline had high standards and experienced operators. If the A300 had any systemic weakness, it would show up there. The numbers that emerged over 6 months left everyone stunned. The A300 delivered fuel consumption per seat considerably lower than that of the Lockheed TriStar, which was the natural benchmark for comparison. 2 engines meant less fuel burned, less maintenance, fewer spare parts, and longer overhaul cycles. The difference in operating cost per seat was significant enough to catch the attention of any CFO. Reliability matched the promises. The CF650 and JT9D engines accumulated flight hours without incident. The aircraft's robust structure, designed with conservative margins and an initial maximum takeoff weight of approximately 137 tons in the B2 and B4 variants,
demonstrated the durability required for high-demand operations. In March 1978, Frank Borman, the Apollo 8 astronaut who had become CEO of Eastern, signed a purchase order for 23 A300 aircraft. The contract was valued at approximately $778 million. It was the largest single order for European aircraft ever placed by an American airline up to that point. It was the first time a non-American manufacturer had penetrated the U.S. domestic market in any significant way. And it was, above all, proof that the A300 was a competitive aircraft in any market in the world. But there was still another element, one that would transform the A300 from a successful product into a permanent landmark in the technical history of aviation. The operational success with Eastern opened doors, but Airbus understood that an aircraft that does not evolve grows old. Throughout the 1980s, the A300 underwent significant technical transformation. The unlinked 600 variant brought changes that reset the aircraft's operational standard. Maximum takeoff weight rose from the initial 137 tons to approximately 171 tons, an increase of nearly 25% that dramatically expanded cargo and fuel flexibility. Range grew to 7,700 kilometers. Aerodynamic efficiency was refined. But the most important change was not in the wings or the engines, it was in the cockpit.
The 600 variant adopted a cockpit designed for just 2 crew members, eliminating the flight engineer position that had been standard on wide-bodies since the 60s. Digital avionics, inherited directly from the A310 developed in parallel, replaced analog panels with integrated flight management displays. It was the first concrete step toward what Airbus would call cockpit commonality, a standardization across all of its aircraft. Any pilot certified on one Airbus model could transition to other models in the family with minimal adaptation time. And then came ETOPS. The A300 accumulated operational data at a scale and quality sufficient to force a revision of the rules limiting twin-engine aircraft to routes within 60 minutes of an alternate airport. With hundreds of aircraft operating on dozens of routes with tens of thousands of documented flight hours, the industry finally had what regulators required: statistically irrefutable evidence. The A300 was the first twin-engine widebody to receive progressively extended operational authorizations beyond that limit, formally paving the way for ETOPS as a global regulatory standard. This new framework made it possible for the aircraft we fly on today to reach any corner of the world. The inevitable question is, why did no American manufacturer see what Airbus saw? The difference began with timing. When Boeing, McDonnell Douglas, and Lockheed designed their widebodies, turbofan reliability did not yet support, with regulatory confidence, a large twin-engine aircraft. Their planes were born within that constraint. Airbus came later and used more mature data to bet on a configuration its competitors would only adopt through a deep redesign. There was also a structural difference. Those who dominate a market can afford to avoid risk. Those entering it must differentiate. For Airbus, the twin-engine design was not gratuitous boldness, it was strategic necessity. And finally, what many saw as risk, 2 engines, regulatory restrictions, potential operational resistance, Airbus treated as a problem of engineering and statistical validation. The restriction was not permanent, it could be expanded with data. The bet was not only technological, but a wager on the willingness to prove in practice that efficiency and reliability could walk hand in hand. The story of the A300 is not about a European aircraft competing with American aircraft. It is about what happens when an organization with no other way out is forced to question assumptions that everyone else accepted as permanent and has the technical discipline to replace those assumptions with data. And the world we fly in today was built on that bet.